Welcome to section 6.2, more trigonometric equations. In this section, we have one objective. Solve trigonometric equations using trigonometric identities. So some trigonometric equations are too complex to solve by isolating a single function. In these cases, we can simplify or transform the equation using trigonometric identities. This allows us to rewrite the equation in a more solvable form, typically by reducing it into a single trig function or converting it into a familiar algebraic structure. Trigonometric identities are like tools in your problem-solving toolkit. So by recognizing when and how to apply them, you can turn a complicated equation into something more manageable. So let's review some of our trigonometric identities. The first set is the Pythagorean identities, right? Where the Pythagorean identities are derived from cosine squared theta plus sine squared theta equals 1. Okay, so all of the identities here on the right-hand side are derived from this first Pythagorean identity. And then our other two identities in this category, 1 plus tan squared theta equals secant squared theta, and 1 plus cotangent squared theta equals cosecant squared theta. The second set of Pythagorean identities, are the reciprocal identities. Okay, so you can kind of consider them like your opposites. So cosecant theta equals 1 over sine theta, and then sine theta equals 1 over cosecant theta, and then all of our other pairs like secant and cosine and cotangent and tangent. The next set are the quotient or ratio identities. This is specifically for tan and cotangent, where tangent is sine theta over cosine, and cotangent is cosine over sine. And last but not least are our double angle identities. Okay, so if we have sine of 2a, that will be equivalent to 2 sine a cosine a. Cosine 2a will be equivalent to cosine squared a minus sine squared a, or 1 minus 2 sine squared a, or 2 cosine squared a minus 1. So cosine 2a has quite a bit of different variations. And then tan 2a equals 2 tan a all over 1 minus tan squared a. So I've provided some steps here to help you in solving trigonometric equations using identities. So your first step should be to simplify the equation using identities. So you want to try to reduce the equation into a single trig function. So converting sine squared x and cosine squared x using the Pythagorean identities. The second step is to rewrite complex expressions. So we can use identities to transform quotients or reciprocals into simpler terms. Step 3, solve the simplified equation. So once the equation is reduced to a basic form like sine x equals 1/2, then we can solve it using known values or inverse trig functions. And then step 4, find all solutions within the given interval. So you want to make sure you list every angle that satisfies the equation in the specified domain. All right, in our first problem here, we're asked to solve for x. Our function or equation is 2 sine x minus 1 equals cosecant x. Okay, and my x value must be between 0 and 2 pi. So that means my solutions must be written in terms of pi. So in this problem, I see sine x and I see cosecant x. And I know that they are related to each other. Cosecant is the reciprocal of sine and vice versa. So I can rewrite cosecant in terms of sine. So I'll have 2 sine x minus 1 equals 1 over sine x. Okay. Now, let's get our sine x in the denominator into the numerator. And to do that, I can multiply both sides by sine x. So when I multiply the right-hand side by sine x, I then cancel the sine x on the right-hand side. Okay, so I multiply this on the left-hand side, and I get the following. Okay. Next, let's distribute the sine x. So I'll have 2 sine squared x minus sine x equals 1. I'm going to write this as a quadratic equation by subtracting 1 on both sides and setting the quadratic equal to 0. I then am going to factor this quadratic, and I will then get 2 sine x plus 1 and then sine x minus 1. I'll set each factor equal to 0. Okay? And I'll solve for the trig function. I'll have 2 sine x equals -1. So then sine x equals -1/2. Over here, I'll have sine x equals 1. Okay, so I'm going to utilize my unit circle to help me identify the angles in radians for each of these factors. So for sine x equals 1, I want to find the angle measurement where the sine value is 1, and that's going to be pi over 2. And then for sine x equals -1/2, so what quadrants is sine negative? That would be quadrant 3 and quadrant 4. Okay, remember ASTC is all students take calculus. So in looking in those two quadrants, I see 7 pi over 6 and I see 11 pi over 6. So the solutions to this problem will be pi over 2, 7 pi over 6, and 11 pi over 6. All right, next equation is cosine theta minus the square root 3 sine theta equals 0. All right, so for this problem, I have cosine and sine. So let's first move each trig function on both sides. So let's move the sine function or expression to the right-hand side. So we have cosine theta equals square root 3 sine theta. Now, why am I doing that? Well, I know that if I move this over to the right-hand side, then I can divide both sides by cosine, which will then allow me to get to tangent. So then I would have reduced 2 trig functions down to 1 trig function. Okay? So let's divide both sides by cosine. This side will be 1, and this will be 3 sine theta. And then I'll divide both sides by the square root of 3. this is 3 equals sine theta over cosine theta. 1. And so 1 over square root 3 equals tan theta. Awesome. Hey, well, tan theta here is positive. All students take calculus. Tangent is positive in quadrant 3 and in quadrant 1. So to help us, we are going to use our reference angle to help us. So let's take the inverse. So this will be theta of 1 over the square root 3. And so theta here will equal 30 degrees. And so this was our reference angle. Okay, now 30 degrees is in quadrant 1. So that means 30 degrees will be one of our solutions. But now we need to find the angle measurement in quadrant 3. So we'll take 180 degrees and add our reference angle to get 210. Okay, and so the other angle measurement will be 210 degrees. And so that gives us our solution. So we used the ratio identity here, quotient identity right here. This was the ratio identity to help solve this problem. All right. Okay. Question 3. We have the equation cosine 2 theta plus cosine theta equals 0. Now, cosine 2 theta is a double angle identity, so we can use any of the 3 that are provided. I'm going to utilize the 2 cosine squared theta minus 1. And I'm utilizing this so that I, 1, have all the same trig functions, and 2, I would have written my equation as a quadratic. And so now I can factor this. 2 sine theta is 1, and then cosine theta is 1. Then set each factor equal to 0. And I'm going to solve for cosine theta. For both factors. Okay. And I now can find theta where the cosine values are -1 and 1/2. So for -1, we know that the cosine of 180 degrees is -1. For 1/2, we want where cosine is positive. So let's all students take calculus. So that's going to be in quadrant 1 and 4. So in quadrant 1, the cosine value of 60 degrees is 1/2, and the cosine value of 300 degrees is 1/2. So theta here for this factor can equal 60 degrees or 300 degrees. So the solution for theta for this problem is 60 degrees, 180 degrees, or 300 degrees. So for this problem, we use the double angle identity here. Double angle identity to help solve this equation. All right, our next equation is 4 sine squared x plus 4 cosine x equals 5, where x is between 0 and 2 pi. So I see here that I have sine squared x, so I can use the Pythagorean identity to rewrite sine squared x in terms of cosine, so then I have all the same trig functions. So I'm going to rewrite sine squared x as 1 minus cosine squared x. And then I'll add the rest of my equation. 4 cosine x equals 5. Now let's distribute the 4 to every term inside our parentheses. In addition to that, let's move the 5 to the left-hand side and set it equal to 0. I am going to do that right off the bat because I know I'll be working with a quadratic here because I have cosine squared x. So now we can simplify the left-hand side. So we'll have negative cosine squared x plus 4 cosine x minus 1 equals 0. We'll divide each term by -1 so that our coefficient a in our quadratic equation is positive. And so now to help us out, let's set u equal to cosine x. So we'll have 4u squared minus 4u plus 1 equals 0. I see here that this quadratic is factorable. Okay. So in other words, 2u minus 1 squared equals 0. Okay. So we can take the square root of both sides, which will just get us 2u minus 1 equals 0. So 2u equals 1, so u equals 1/2. So back substituting, cosine x equals 1/2. Now cosine is positive in quadrant 4 and in quadrant 1. Okay, so we want the angle measure in radians whose cosine is 1/2. So in doing that, we will get pi over 3, and we will get 5 pi over 3 as the two angle measures whose cosine value is 1/2. All right, and so in this problem, we used the Pythagorean identity to solve this problem. Okay. All right, let's do one more. Our equation in this problem is the sine of 2 theta minus sine theta equals 0. So I see sine 2 theta here, so I know I'll be working with double angle identities. So we can rewrite sine 2 theta as 2 sine theta cosine theta minus sine theta equals 0. Both of the terms on the left-hand side have the sine function, so let's factor that out. So that will give us sine theta times the quantity 2 cosine theta minus 1 equals 0. Since it's in factored form, I can now set each factor equal to 0. So that will be 2 cosine theta minus 1 equals 0. So I have sine theta equals 0. And then over here, I'll need to get cosine theta by itself, which will be cosine equals 1/2. Well, I know theta will be 0 degrees and 180 degrees for when sine is 0. And then where cosine is 1/2, we did this on the problem before, where we got pi over 3 and 5 pi over 3, which in degrees will be 60 degrees and 300 degrees. So the values of theta that make this equation true are 0 degrees, 60 degrees, 180 degrees, and 300 degrees. Okay, so in this problem, we used the double angle identity in this problem. All right, great. And that concludes section 6.2.